Hello, everyone, and welcome to the Extreme Performance Series, Efficient, Sustainable, and Performant. Have your cake and eat it too. My name is Valentin. I'm a senior staff engineer with VMware. I've been working here for a little bit more than 11 years, and I'm in support in the Premier Services division. And for the most part, I deal with resource management and performance. And usually that is to fix performance issues. But what I want to talk to you about today is how can you get the most out of your environment? Do you really need all of that performance? Would you rather have more density? Would you rather run more efficient? Can you be sustainable at the same time, right? So let's just skip the disclaimer here because we really are not going to talk about anything relevant here. So this concept of extreme performance, I want to ask whether we can also think about extremely appropriate performance or extreme appropriate performance. And if you have watched the performance best practices last year and the year before, you will have seen most of what I'm going to talk to you about. But I think it was time to move it out into a separate session so that we can talk about other performance stuff in the performance best practices session, and that we can concentrate here on how we can make stuff more efficient, right? Because it doesn't always have to be performance tuned to an end. So when we configure our defaults, right? So when ESXi ships and you create a VM, usually what we try to optimize for first and foremost is stability, then security, then performance, and then consolidation. Now that ratio might not fit everyone's needs, right? Maybe you want to give up 5% of performance for 20% of consolidation, right? And there are certain options that make that possible, right? Just because we ship with it doesn't mean you have to run with it. But discovering these options and figuring out whether the risk is worth it or whether there are any other side effects is usually very hard. So I want to address some of these here. What can we do to help Captain Melvin? If you're asking yourself, who's Captain Melvin? That was the superhero joke that I had initially in this recording, but apparently it wasn't quite on brand. So if this session isn't funny enough, watch the performance best practices from last year for the 30 seconds of joke that I had to cut out. In any case, what you can do is not to run it, right? If you want to run more sustainable, don't run them, But what I mean with don't run is don't run everything, right? Don't run the things that you don't need to run. And one of these is zombie VMs. So there are probably projects that have long been forgotten, people who have left VMs that are ownerless and actually benefit less, right? I'm not sure whether we have talked about this in the past, but VMware did a data center migration, and we have discovered tons of VMs that were no longer necessary. Most of them were discovered that it didn't have an owner. If they had an owner, they were decommissioned. For some others, we screen tested, right? Turns out that very few people screened. So in most environments, there's going to be tons of VMs that you don't need any longer, and you might want to look into addressing those. VROPS has some very limited capability to look at CPU usage, but ultimately it is down to how good your life cycle is on how many zombie VMs you still have in your environment. Use distributed power management. And you might be saying, you better not, you must be joking here, right? And I'm not. Despite its bad rap because of, I'd say, some missing features in the first iteration, it is still beneficial. Now, it actually makes a lot more sense with what I'm going to talk about, because then you will not have some of the impact, meaning contention, high cost of memory reclamation, that you might have had before. It's only one minor aspect or one minor risk, but you can definitely reduce that. But we're not going to talk about DPM exclusively, or actually at all, besides this mention here. Look into it. It is still a great feature. It is not forgotten. It is still working. Now, what I want to concentrate on is on the run as efficiently as possible, right? And that is utilize low risk power management, right? It's not necessarily just conserve a lot of power and have no performance, or have tons of performance and don't conserve any power. There is a path in the middle. And I would argue not really in the middle. It's actually very much towards maximum performance and still very much towards lots of energy conservation, not conversation. We'll have a conversation. We conserve power. Transparent page sharing. Despite many people claiming it, transparent page sharing is not dead. It isn't off. It is still there and working just fine. It's just working different than it used to due to some technical things that have happened, many of them. And we're going to go through every single one here. And then right size. Now, when I talk to engineering, right, and they say, why don't they just right size their VMs? Very often the actual effort and the amount of talking to people, other people you have to do to right size is just not worth it. The cost of right sizing is just immense in stress and in effort, right? So usually right size for me is, yeah, sure, I'll let you right size that. Right size this, right? In any case, we don't want to talk about right sizing. We will talk about power management and transparent page sharing. To be on the same page, we all have seen this here, right? That's the HTML5 client, has a bunch of VMs, right? And what we might be looking at, or what we might be seeing when we're looking at our client list or our VM list, is our highly fine-tuned performant VMs that strive for a certain purpose, right, over the finish line as fast as possible, right? But that's not really what most VMs are. Most VMs are more akin to a cab that you need to take to get to the airport, and you don't want them to pay. And it's okay if it takes 20 minutes, right, and you pay $20 or $30. It's not okay if it takes 15 minutes and you pay $2,000. I mean, for some people it might, but again, that is a minute amount of instances where that would be relevant. For the most part, you want a cost-efficient service, right? So how can we get the most cost-efficient service for our VMs, right? How can we make our VM a little bit closer to price caps? So one aspect of power management, or one aspect is power management, right? We want to consume the right amount of power for the right amount of work. So, but power management is a massively complex umbrella term. So there's all of these technologies under that umbrella that all play a role, and all of them are minor contributors to what some people think power management impact is, right? Yeah, all of these technologies in some form or another can have an impact on performance potentially. But the big hitter, right, was p-states. I mean, is still p-states, right? I mean, if we have a case or a performance escalation and power management is at fault, 99% of the cases, it's still bias-controlled p-state heuristics. Yes, sometimes it is that the PCIe power management was turned off and the I/O devices didn't give as much throughput. That's possible. Sometimes it is the QPI frequency. Very rarely, very, very rarely, that is the deciding factor. That maybe sometimes be 5% or 3%. P-states, sometimes 30, 40%. So that's the main one. The other one that we want to talk about are deep sea states. Now these, despite their name, idle states, are actually fairly important to gain performance, not just to save power, but also to gain performance. That is our eat your cake and have it too setting, so to say. So let's just go over the technologies really quick. Well, not really quick, a little bit quick. P-states are voltage frequency point, meaning that you do not really have like a gradual frequency across the whole spectrum, let's say from 3 to 0 gigahertz, right? They're predefined steps depending on the vendor. For example, AMD Zen, actually, they only have like 3 P-states, so a lot larger in regards to the P-state voltage frequency points they have. Here we're looking at some Intel CPU with a lot of P-states. Usually the highest P-states, so P13, is approximately half the nominal frequency of the CPU. And whenever the CPU is executing something, that is called a P-state. And it's also called a C0 state. And that's the only idle state that is non-idle, meaning the idle thread isn't running, it's not halting, M-waiting, whatever. So frequency matters when we're executing. When we're not executing, we idle. And idle does multiple things. It actually turns stuff off at varying degrees depending on how deep you idle. So here we're looking at an Intel Nehalem, so fairly old CPU. On the left-hand side, we see a heat map, so everything is working and executing, and obviously the CPU warms up. On the right-hand side, you see my artistic representation of how that would look like if everything was idle, except the caches. So C1, the most shallow idle state, is called a snoopable idle state, meaning all the cache coherency is still working, meaning the caches have to have power. And that the graphic original was from a C6 state, so I just superimposed the caches. I bet it's wrong, but it's probably closer to being right than well, no, it's probably just wrong, but you see the caches there. So that's the C1K, the C1 state, and the wake-up latency is approximately 1 microsecond. 1 microsecond, is that a lot? For a CPU, it actually is, but it's also not a lot in general, right? So depending on how many C-state transitions you make, how sleep-heavy a workload is, the more impactful that can potentially be. For some, it is, but again, those are minute percentage of applications where you actually would, instead of idle, you would pull, right? And you just wouldn't hold. Now, a deep C state here is the C6 state. And you can actually see that everything is turned off and everything is flushed into higher order level caches here. And the only thing you see is the temperature sensor that is still in every core that is still active. And for this particular CPU, the wake-up latency can be as high as 30 microseconds. Actually, on some Broadwood CPUs, it's 40. Now you might think that is a lot. Why would I do that? I mean, wouldn't my performance would my performance decrease? And well, first of all, the operating system, ESXi in this case, would only ever use a deep C state if it would think it would stay in that deep C states long enough to make a benefit, right? So if the wake-up latency is very high, ESXi would never go into a deep C state. Also, if you don't really go into a deep C state very often, you don't take that overhead very often, right? I mean, an overhead is only as bad as the amount you take it. If you only do like 100 transitions at 30 microseconds each, that's not really an overhead, right? If you do 10,000 on the other hand, and it always goes to the deep C state, that's a different story. Luckily, those workloads are very, very rare. The workloads where you hit that sweet spot between the operating system actually idling so deep and then waking straight up, very rare, very far in between. So as an example, what we usually recommend, and this is for performance and sustainability reasons, well, more performance and sustainability, right? Our goal is to reduce risk as much as possible. So while we all, I think, agree that efficiency and sustainable is important, right? Risk to the business can undo all of that effort. So the most important part is to keep it risk-free as much as possible, or to reduce the risk as much as we humanly can. Now, sometimes when you get a server delivered, it has a policy configured similar to the performance per watt policy here that we see here. And it actually has P states set to what is called system. I think I can't think of the full name anymore. Okay, DBPM. Based power management. Dynamic base power management. I feel like I should know this, but it's not important, luckily. So I hope you can forgive me. So with that setting, the ESXi host is the ESXi host. The BIOS is controlling the P states, and very often that is a little bit too conservative. Meaning the P states that are being set by whatever heuristic the BIOS is applying is a little bit too extreme. Very often it can be that even though most of the cores on a socket are active, the frequency is basically reduced to 50% of the nominal frequency. Now, there are many different heuristics, and it depends on the CPU model, it depends on the vendor, but very little. Most of these vendors, whether it is Dell, HPE, Lenovo, Fujitsu, we have seen that with pretty much every vendor, right? Those dynamic power management, or not even the low power conservation policy, just the medium or dynamic one, they usually are a little bit too harsh when it comes to conserving power, and they usually use P states a little bit too much. And P states aren't actually all that efficient anymore. So that kind of makes it even worse. So you're not actually saving that much energy when you just pay a price in performance. So what we usually recommend, right? So most people would go from, let's say they had a bad experience with the dynamic power management policy, and they say, I'm going to go to the max performance policy and nothing can happen to me. And that's a safe choice. But what it also does, it disables deep C states. And why that is a problem, we'll get to in a second. What we usually recommend is that you do a custom policy where you apply the exact same settings as in the high performance policy, but you change P states and deep C states to be controlled by the ESXi host. Because when you control it with the ESXi host, you can enable it and disable it whenever you want. So in theory, if you don't like what you're seeing, you can always just set it to a high performance policy in ESXi, upon which we then no longer will use P states or deep C states. You couldn't do that if you decide to do a high performance policy and then just configure something on the ESXi host, but we get to that in a second. So if you configure a technology in the BIOS, the two that we can detect are P states and C states. And if we detect them, you can see them in the power management screen. Now, this is actually still a 6.7 screenshot, and I realized I should have changed that to 7.0. Now, power management is actually hidden under hardware overview. It's very hard to find. You have to scroll down. I wasn't very happy about that change because it actually took me like a minute to find. But you see the technologies that the BIOS currently is presenting. And then you see our active policy. And our active policy really just tells you whether we are going to do anything with those technologies. Default is balanced. With regards to control, right? The BIOS actually enables us to see P states and to see deep C states and to control them. So the BIOS has to offer basically via ACPI. It says, hey, here are the technologies that you can control, and ESXi then controls them depending on its policy. So if the high performance policy set, we don't use P states, we don't use deep C states. The balance policy set, we will. And you could even set up a custom policy where we don't use deep C, where we use deep C states, but we don't use P states. So the guests actually, they don't really know about any power management features. All they can do is halt and we deschedule them, right? Our power management runs when the ESXi is running its idle threads, right? So when no VM needs to run. So if you want to pause this video, or if you're already looking at this on one screen and on the other screen you have your vSphere client, check what technologies you see. If you currently see ACPI C states, that most likely means you're running it at a dynamic policy, because that presents deep C states to the OS and it controls P states, but it usually over controls P states. If you see nothing, then most likely running at a high performance policy, because that doesn't show the OS operating system deep C states or P states. Now, obviously, there's many different permutations based on policy, or if it's a custom policy that you could be running it, but these are some very likely explanations, depending on what you see. No guarantee, of course. So what policy am I running at, right? If you actually SSH into one of those ESXi hosts where you're not sure, despite the technologies you can see, if you're on dynamic, you will most likely see that A, you do not see any P states. You do see that ESXi sees deep C states, and here we call it C2. In reality, it's C3 or C6. C2 in ESX top just means anything deeper than C1. And you see APerf, MPerf. Now, APerf, MPerf is actual and measured performance. You actually have to activate that. So press F in ESX top, press F again for APerf, MPerf, and now you can see the frequency in percent against the nominal frequency. And here you're definitely being downscaled across the board. Now, in the performance policy, you still don't see P states, you don't see deep C states, and you see that the nominal frequency should be above 100, because in any modern CPU, you probably have some turbo boost. And if you don't know what turbo boost is, we'll get to that in a second. Now, if you're running a custom policy, what you will be seeing is all of the different frequencies of the P states. You will see deep C states, you will see all of the P states, and you will see APerf, MPerf. Now here we're also running below 100, but again, this host is completely idle. Now ESXi, when ESXi uses P states, reacts immediately to just a little bit of load. So instead of running at the lowest possible P state, we immediately ramp up to P0 if need be. So talking about turbo boost, a turbo boost is nothing but a CPU vendor sanctioned overclocking, meaning that if there is thermal headroom, we will run at a higher, or the CPU will run at a higher frequency. Now that is happening in steps of the, in multiplier steps of the front side bus. So if you have a 2 gigahertz CPU and you have a 100% front side bus, then every turbo bin is 100 megahertz more. And there is a certain limit to how many default turbo bins all cores can have at the same time. Now, if you deep idle some cores, the remaining cores will get more turbo bins, meaning the less cores are active, the better performant the remaining ones are. And if you turn off all but 2, they will have the maximum amount of turbo bins. So especially if your host isn't highly utilized and you have applications that depend on single threaded performance, turbo boost is very beneficial, right? Now this concept, so why would it be power efficient, right? Because it seems like turbo boost isn't that isn't usually running at high frequencies energy inefficient? And yes, you would be right. It is energy inefficient. There are even technologies that cap the maximum rate of turbo bins based on, so you don't run too inefficient. But the point is that it is also very performant. It is also very performant to just race to idle, meaning you go somewhere as fast as you humanly can, and then you idle as deep as you possibly can. Plus, it gives you the choice. Having deep sea states and having the max amount of turbo speed gives you the perfect balance between having performance when you need it and giving you all the idle capacity, the idle potential when you don't run as much. Right, and given that there usually is an ebb and flow between high loads and times where you don't need that type of performance, you'll have the best of both worlds. And that is working out pretty good for the most part. So if you look at our power management policies here, those are the advanced power management settings, and they're mapped to the individual policies. And if you look, let me just go back. If you look at balance here, the max CPU load, this is how fast we react. So if any core gets utilized at 60% or any vCPU, we immediately, and this is not necessarily for your 20-second average. Immediately, if there is any load past 60% over a very, very small sample, we immediately switch to P0. So the reaction is very fast. There's also max frequency percentage that is set to 100. Now on Intel CPUs, if you set that to 99%, you disable turbo boost. So if you want to know, hey, how much do I lose by disabling turbo boost with regards to performance and energy? If you allow ESXi the control, you can turn it off, right? One setting, one line of PowerShell, 2 lines actually. Or you can also make it 1, right? But so it's very simple. You don't have to reboot. You don't have to go into the BIOS. It's very straightforward. So what I'm saying is, if you're right now on a BIOS, a dynamic policy, especially if it's an older CPU, and you shouldn't be, I hope you're not on anything pre-Haskell, that's not good, because for the most part, you probably will be running massively frequency scaled. If it's post-Haskell, when Intel switched to per core P states, chances are that it's a little bit less impactful, but it can still be massively, your frequency can still be massively reduced. If you just switch to the high performance policy, on the other hand, you're probably pretty safe. You definitely will have the performance, but you won't have deep sea states, and you probably will consume more power than you actually need. Also, you will not have those high turbo frequencies. Excuse me. So the optimal configuration really for performance and for efficiency is to run a custom BIOS and set it to all of the policies that you would in the high performance policy, to all of these settings, and to configure P states and deep sea states. So now you might be saying, well, I did that in the past, right? And I switched from dynamic to custom BIOS, and it definitely was not as fast as when I set it to the high performance policy. And well, no one is saying to switch it from dynamic to a custom BIOS. What we've been saying is switch it from dynamic to performance to custom BIOS. So basically, you will be running at the performance policy just with ESXi, controlling P states and deep sea states. Now there is minor differences. There's C1E, but that should barely play a role. Sometimes when we've seen differences, even with the second configuration and performance, it is usually, or it was in 2 cases already, a BIOS issue where the PCIe management was not configured to performance when a custom BIOS policy was enabled. So that can happen. Apart from that, if you configure everything but C states and P states to performance and you disable those in ESXi, it is exactly the same as the high performance policy. So you can always disable it. Again, control. You can easily control what you want to achieve. You can disable turbo boost. You can disable deep C states if you want. And that wouldn't be possible if you would just be relying on the BIOS. Okay, so now, but you're still saying, oh, come on, if I set it to high performance, I won't have any issues, right? And that's not right. You still face the same issues. There's a tiny little bit of risk that you voiced, and that is minimal. So minimal that I'm telling you, it's outweighed by not having turbo boost and not having those deep sea states. Because if you have any PSU issues, power capping, temperature, firmware bugs, and those happen quite often, you will still have power management issues. Again, running below nominal frequency. That is the most common cause of issues. And again, you will not have deep C states, you will not have P states, and you will not have those sweet, sweet turbo boost frequencies. And on how much you're missing out, you can actually check out in the Intel specification updates, where you can see how many cores have to be active or have to be idle, and what frequency they can reach. In this example, the difference between just 1 and 2 cores being active to all cores being active, the difference is 500 megahertz, right? And this is, there are examples where the difference is 300 megahertz. There are examples where the difference is 1 gigahertz, right? So your mileage may vary. Okay, let's switch gears a little bit. Let's go from, I was about to say let's go from CPU to memory, but actually the CPU is still heavily involved. So let's just say, let's go to memory. So usually I would be asking questions and I would be counting hands that go up, and approximately to get a feeling. It's not really possible. I don't actually know whether there's any sort of feedback mechanism besides the rating. So I'm just going to ask these questions and you pretend you talk to me. Do you overcommit in memory? Do you also overcommit it in production? And what is your ratio? These questions were asked before. And actually, I'm just saying that down there should be saying VM assigned to physically available. So meaning what you give your VMs and what the host has. Kind of slipped through here. So these questions have been answered before, and they were answered in 2000, asked and answered in 2008. So what do you think those questions were answered with in the past? 57% answered with yes, they overcommit memory. Usually nowadays that ratio is a lot less. 87 out of those 60% says yes, they overcommit in production, and the average overcommit ratio ranging from 1.4 to 3 was 1.8. 1.8. When is the last time you saw an overcommitment ratio of 1.8? And if you tell me you have one, then you're the exception, because this is not very common. So let me ask you this question here. If you had the opportunity, right, to transparently, hint, hint, reclaim a large amount of VM memory, but you might run a risk of a performance impact, not much, but a little bit potentially, but you could always really easily undo that, and it wouldn't really take much. So no complex reboots or anything. Would you press that button? Now, I hope some of you would, and if you would, then you can actually skip to the end of this and you don't have to listen to me talk. If you don't, then I hope you stay with me a little bit longer and try to make my case on why you should press that button. So let's rehash transparent page sharing. Full disclosure, since this is a sustainability session, I reused this bottle, right? I actually have like a hard plastic somewhere around here, and this is an old bottle. I've refilled this multiple times. Again. So transparent page sharing. Transparent page sharing runs consistently in the background. It is not dead, it isn't turned off. The pshare thread or the world consistently runs, and it will check for hashes or will constantly generate hashes for guest small pages. We do not hash guest large pages. So if you have, for example, transparent huge pages on Linux, we won't touch those. But if they're small, fair game. Even if the pages are backed large on the ESXi side, we still hash all of the small pages in that ESXi large page. But we do not share them when they're in that large page. So we know whether we can share them or not, but we don't share them. Now here's the thing. There isn't really an easy way to figure out how many of the pages that are in those large pages are shareable. There is a way, but it's not straightforward, and it definitely isn't easy to see. So these large pages are broken at what's called the clear state, and we're going to talk about that a little bit later. That has happened since ESXi 6.0. Before that, they were only really broken down at a soft state. So right at the time, we'd also balloon. By default, they're NUMA local. There is a setting to actually not make it NUMA local, but it's most of the time it's not really worth it. But if you want to, if you think you want to go that far, you couldn't change it. I'm not going to tell you the setting. If you just list the settings and you look for NUMA in page, you'll find it anywhere. And for the past few years, you can only share within a VM, right? So we disabled inter-VM sharing by default, and we only allow intra-VM sharing for reasons that we're going to get to in a little bit. Also, most of the time, the 0 page is the most common one. So that is usually the biggest shared page. So if you have, let's say, 2 gigabytes of 0 somewhere, 2 gigabytes of pages worth of 0, that all will be represented with a single 4 kilobyte full of zeros on each NUMA node. But we were just saying, right? While we transparent page share, we do not transparent page share with large pages. So let me walk you through what happened. So I started at VMware in 2009, and since that time, right, page shared, page saved has constantly gone down, right? I mean, maybe you remember the early times of a virtual environment where you overcommitted at your heart's content, and you would start another VM and another VM, and they all had like 10 or 4 gigabytes of memory, and your consumed memory would only increase by 1 gigabyte, and you would be super happy. That's not happening anymore. But there are good reasons why it's not happening, and we're not just making this for fun. There is a reason why this happened. But pages shared and saved went down, memory consumed went up. And the reason for that was not one thing, it was actually multiple things come together. One was a hardware change. Now CPUs included hardware page tables, so nested page tables. Because of a certain overhead there, we had to use more host large pages. Then there was rowhammer. We had to use only intra VM or page sharing. Windows became more caching aggressive, meaning that instead of having tons of 0 pages and free pages, all of a sudden, all of that was memory mapped files that are rarely shareable across VMs because usually the files differ. And Linux also introduced huge pages, transparent huge pages, which again, we don't hash. So because of that, and because these changes kind of happen at the same time, and sometimes they happen from a patch. So there was one specific patch on 5.5 where we would back more aggressively with large pages. So all of a sudden, you ran the same VMs, you maybe did a hardware change, you maybe upgraded an OS, and all of a sudden your memory consumption would explode. You would balloon, you would swap, and all of a sudden you think, wow, I need more hosts, right? When in reality, the ballooning and swapping reaction came a little bit early, and that's why we introduced the clear state. Let me go into a little bit more detail. So Windows Server came out 2008, but usually Windows 2003 dragged along for a very, very, very long time, right? So the density of 2008 to 2003 only somewhat went down, let's say in 2000, I'd say even 2011. So at this stage, there was probably still a good mix of Windows 2003 VMs, which had a very high share ratio. Now, when AMD introduced Barcelona, it had the so-called rapid virtual indexing feature. It supported nested page tables. Intel, first CPU that supported Intel page table, nested page tables. And we were making use of that, of these nested page tables for certain VMs, right? So there were certain monitor modes for certain VMs, depending on what the performance benefit potentially could be. And because of that, we were making more use of that technology. Then Intel Linux introduced transparent huge pages. They were only made default in Red Hat Enterprise Linux 6. I'm not sure about other distros. But again, for many applications, they're turned off for certain reasons. And then with ESXi releases, we became more aggressive with how much we back with large pages. So all of these things kind of came together in a perfect storm to reduce at least the perceived consolidation ratios, right? Because again, transparent page sharing was still working, but it wasn't active on default anymore, right? And when rowhammer came and we disabled inter-VM page sharing, people just thought it was dead. And the reason why I remember this so well is because I started in the middle of this. So this is my, I've explained this once a week, I'd say, for a year or two on why there were certain amounts of ballooning or certain amount of swapping. And I hope I can kind of capture that here again, and why it also isn't that much of an issue, I'd argue. Now, what we did as a response to that ballooning and swapping, we introduced the clear state And we also introduced unswap. Unswap isn't really supported, but it's basically an option that you have to unswap memory. If you Google unswap vSphere, you'll find it. In any case, we introduced the clear state because clearly there was a problem with too much or too early or too late large page breakdown, and we were ballooning and swapping too early. Now, ballooning usually not an issue. What's usually the issue is that ballooning is very brief, and then if the memory allocation is too large, immediately swap. So people kind of people usually are averse to the performance impact of swapping. Ballooning is just a metric that happened to happen at the same time, because for the most part, ballooning doesn't have that much of an impact. So with that being said, let's look at our memory states. I hope everyone still remembers what min-free is. Min-free is that amount of memory that ESXi always tries to keep free. That 100% is a sliding scale of memory depending on the host size. Let's just say it's between 2 and 5 gigabytes, right, depending on host size. And ESXi always tries to keep that free. If a VM allocates into that, ESXi will reclaim memory, not necessarily from that VM, but from any VM that has the least entitlement. And it will break large pages, it will balloon, it will swap. Depending on how far you reach into that min-free, depending on how much it is depleted, ESXi will become more aggressive and more aggressive, right? So when I'm showing you that here, hi, we share, that's not really true. I mean, we just went over that. They're large pages, meaning we hash them, but we don't really share. So that's actually not really true. It is somewhat true. Like if the large page pool is exhausted, there's too much fragmentation and there are no more large pages available, then yes, there is transparent page sharing still happening at high. But usually that is very rare. So what we did is we introduced the clear state, which basically now pushed min-free out by 300%. So now we start breaking up large pages, let's say it between 6 and 15 gigabyte free memory, right? So whenever you reach consumed 95, 98%, that's the time we break down large pages. If it goes further, we balloon, then we compress, then we swap, and so on. So a good analogy, I think, I mean, it definitely was last year. Right now, I don't know. I don't know what an airport looks like anymore. But if you look back and into the days where we could travel, and the runway and the stopway, and you know where your runways, where you land and take off, the amount of non-min-free memory, that is the runway, right? And the stopway is just after the clear. It's just after it's just after the high state. So that's where you can still roll. There's still concrete there. That you're a little bit over. And then there is the clear way, the green, the grass, right? Usually you don't want to go there with the plane, right? Because then the legs are going to break off and everyone is in for a bedtime. So that is when ESXi starts aggressively memory reclaiming. And I'm trying to put this together here. So if you have a runway, the available memory is a runway, all is good, right? That's what we want to see. And as soon as you reach the last part, the stopway, that's where we break up large pages, because usually breaking up large pages, performance impact. It is, okay, we'll talk about the performance impact later, but usually large pages, for the most part, have the least performance impact. There are some corner cases where ballooning in theory has less, depending on what you're doing and what the workload is. But let's not overcomplicate this too much, because it already is complicated. So let's just say large pages, least performance impact of all of those reclamation technologies, even though there's always a special case where it really doesn't hold true. So if we blow this out a little bit, if we transparent page share, so breaking large pages, right? And if we balloon out the available memory, so free pages, 0 pages, standby list, and so on, that has very little impact. And then once we start to balloon out the working set and we swap on the hypervisor, that's where you go into the grass and you don't crash, but unless you have host to SSD swap, it's going to be ugly, right? So you usually want to avoid that. Again, you don't have to avoid that if you have low latency local devices and you can do swap to SSD or actually use the host swap cache, then swapping will not have the same impact. It will be dramatically improved. In any case, let's just assume you don't have that. You want to avoid it. Now, usually you can, depending on what your VMs are doing, you can TPS Transparent pager, a different amount of memory, right? And that depends on what's going on in these VMs. The thing though is that that point where you consume memory and the point to where transparent page sharing breaks down large pages and you transparent page share more and more and more is 95%-ish consumed. If you even start even more VMs and you have even more transparent page sharing, how much memory do you think you consume over here? 95%. What about over here? You start even more VMs, there's more reclamation happening. How much memory do you consume now? 95%. It is very hard to eyeball where memory is actually being used for just based on that one metric. And yes, it is complicated and it's not easy to see in the UI. You would be looking at reclamation metrics. You would be looking at assigned. You would be looking at memory demand. And let's not go into all the metrics because that just gets more complicated, and whether you should rely on active or whether you should be starting at guest mem needed and VROPS and whether that is too conservative. A whole other discussion. What I'm trying to say is it's really hard to see how much memory is being reclaimed and how much you could reclaim with transparent page sharing or ballooning just based on the consumption metric, right? If you look at it, it might look at this with 20 VMs or 30 VMs. You cannot actually tell whether you are not overcommitted or whether you're massively overcommitted. This is not a good gauge. And I usually compare that to a guess gauge, right? And let's just assume available fuel here is available memory, and it just drops down to a certain amount and stays there. So imagine you're driving on the road, the needle dips into the red, and you're like, oh, I probably should go to a gas station, AKA buy a new host because my memory is running low. If you're talking very basic capacity planning, and you're driving on, you deploy more VMs, the needle doesn't move anymore. It's like, huh, that's odd. So you look into the documentation, but you can't find anything. So you ask your colleagues, but they haven't been working with VMware for long enough. So you call support, they say everything is fine. And then you find some old guy in the back that says, oh, no, I remember where that is from. That's a feature. So basically what we're going to do is we're going to run more efficient until you're basically running on fumes, at which point you will probably drive a little bit slower, but not much. But once you reach that point where you're driving on fumes, we just stop the car and maybe the engine starts burning. What would you do? Would you risk that? No, you would go to a gas station and you would fill up the tank, right? You would buy a new host. Who in their right mind would trust that? A little bit harsh, right? You can definitely trust that. The problem is it is hard to trust without insight, right? I always say that transparent page sharing lacks transparency. You cannot see how much you can potentially share, right? Yes, everything is fine. Transparent page sharing will react. ES6i will work its magic. It will transparent page share what it can, then it will balloon, then it will swap. And it will do so based on the entitlements of those VMs. So how active they are or whether you have reservation set, it does that. And it does that very well. But again, you just don't know what it's going to do. And I think that's a little bit of a problem when you're trying to plan and when you're trying to capacity plan. So why large pages? Now you're saying, okay, what I've heard so far is that host large pages makes everything complicated and I want my life to be as easy as it was without them. Well, yes, it definitely was easier, but there is a reason why we're using host large pages. Now I'm going to tell you why we're using host large pages, and then I'm also going to tell you why you don't necessarily have to use host large pages. But I want you to understand that we had very, very good reasons and still have very good reasons. This stuff is important. It is just not important for everything. And it's not as important for most workloads, it turns out. So I'm presenting here and recording on my laptop, right? And I have more than one process running. I have multiple processes running. Like, I don't even know how many, hundreds probably. Every single one of these processes has 256 terabyte of virtual memory. Now, I don't know about you, but I don't have 256 terabyte of virtual memory in my work laptop, nor in my private PC. So what happens? Magic happens, right? Some sort of abstraction happens between those virtual memory address spaces and the actual available physical address space, right? The ability to overcommit, yet still separating security between processes and making it one contiguous, isolated address space for every process, right? Now, in ES6i, I run more than one VM. I run multiple VMs. Those VMs have a maximum assignable amount of 6 terabyte. Now, ESXi works its magic to abstract, to overcommit, and to fit that into 16 terabytes of host assignable memory. And then there's other technologies. And obviously, we have tons of potential swap. Now, that is depending on different configuration maxima, but there is not as much memory and physical hard disk space available as you can assign to VMs based on the maximum number of VMs we support. So we have other technologies like transparent page sharing and compression and ballooning, but ultimately virtual memory to physical memory is abstraction, and VM physical memory is just ESXi virtual memory, right? It's just another layer of abstraction. So what we have to do, right, even on bare metal, is we have to abstract those, we have to translate those virtual addresses to physical addresses, right? So the guest virtual address translate to virtual address. Because again, every process has their own complete virtual address space, and we have a limited physical address space. Now, this is not just a list where every virtual address is a physical address, because then the list would be as big as the memory, right? It just doesn't make sense. So it works a little bit different. If you look at this address here, what do you see? And you can pause this, so I don't have to wait because time is running out. Pause. You can see is that the last bit is actually the same. So if you look at a guest virtual address and you look at the physical address, you will see that some parts are the same. And that is the offset into the page. So if a standard 4 kilobyte page, you need 9 bits to address any possible byte within that 4 kilobyte page. What comes before that is the address. And you only need to translate that address bit to the physical address bit. The offset always stays the same. And that's important. You have different sized pages, and these are predefined by the CPU, right? So on x86, we have 4 kilobyte, 2 megabyte, and 1 gigabyte. And it's not a coincidence that they're all 512x of their former page, right? Anything in that page, or anything in that page has to be addressable by the number of bits in the offset, right? You still have to be able to address a single byte. That's why it's called byte addressable memory. So you need more bits to address that massive offset of a page, right? And as you can see, the bits that you need increase by 9 for every page. So for 1 gigabyte page, you need 30 bits to address every single byte. Now, what does that mean? Well, if you increase the page size, you increase the offset, right? And the offset always stays the same. Since the offset always stays the same, you don't have to translate that. You basically, if you increase page size, you decrease the address size that you have to translate. And while the number of bits are not accurate here, right, it's just an approximate approximation of how much of the offset remains. Okay, so what work is involved to go from virtual address to physical address? Now let's start out at the highest level, 256 terabyte. That is represented by a single small page size table, right? That basically has entries. Now every process has their own page table, right? Every process links at that structure there and will build its own page table for its virtual to physical mapping. Now at that level, right? Again, it's 4 kilobyte in size. It has 512 entries. 512, we've seen that number before. And those 512 entries point at other tables that are also 4 kilobyte in size, and 512 times 512. Right? Those tables then furthermore point at other tables that then point at other tables where the entry points at another table, and so on and so on and so on. And you can see how we're moving in increments of 512 because every single one of these tables has 512 entries, and every one of these entries is a physical address to another table contained within the table. So these page tables actually contain potentially consume a good bit of physical address space already, right? And if you look at your memory stats, you can usually see a size for PTEs or physical page tables or page tables. So basically, this is tracking in a hierarchical structure, right? Where the relevant where the relevant mappings are. And just so you can concentrate on that, if you're going from 512 gigabytes to 1 gigabyte, you can either point at other paging structure that can then point at 2 megabyte pages, or it can directly map to 1 gigabyte page. And the same goes for 2 megabyte pages and for kilobyte pages. And what I hope you can see here clearly is that the amount of physical addresses that you have to touch goes down if your page size is larger. So the larger your page, the less you have to jump around in that page table. And jump is basically physical memory access. So let's look at this. Let's look at the page walk from another point of view. So the TF3 is a register that points at the processor's page table. And the first bit points at the page table, right? That's always going to be there. Now look at this, the linear address up there, the virtual address. The first bit or the first few bits point at an offset in that page table. That offset in that page table contains a physical address, and that physical address points then at the next page table. Now, the next part of the virtual address is an offset into that page table, and that offset contains an address that then contains a physical address to the next page table, and so on, and so on, and so on, until we reach the offset, which is an offset into the last page. Makes sense? I know it's complicated, but what I'm trying to say is, or what I'm trying to highlight is that, again, the smaller the page, the more of these physical memory accesses you have to do to actually find the reference, the physical reference to that page. Now, that seems cumbersome. It is. It's actually fairly CPU intensive to walk a page table. So there are certain structures to avoid having to do that. And that's called a translation look-aside buffer, the so-called TLB. A TLB is a two-way cache, meaning it maps one address to another address. Again, the offset stays the same, so it only maps certain parts. A TLB is limited in size. It's a cache. It's not endless, right? So it only keeps certain pages. And if you touch different offsets in the same page, if you stay local to a certain page, like if you touch 8 different bytes in a 4 kilobyte page, right, then you do not have to retranslate that page. At some points it drops out and you have to retranslate that. And obviously the larger your pages, the more entries your TLB can hold. And there's different TLBs for large pages, and it's complicated. So let's just try to look at what a TLB does. So as I mentioned before, it has a virtual part, has a physical part. The offset stays the same, right? Now, here we basically were just looking at bare metal, virtual to physical, right? But what if you virtualize? Don't we have another layer? Don't we have guest virtual, guest physical, and machine physical? And you would be right with that. So what's happening with my slides here? So what you think might be in a TLB is guest virtual and guest physical, but that's not what's happening. It actually goes directly from guest virtual to machine physical. So the guest physical part is completely skipped. So that is how the TLB and virtualization in general can retain that performance. Because if you would have to do the translation every single time within a virtual machine, that would be really, 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 really slow. So that is what you need. But for that to happen, you have to walk that page table multiple times. So to fill that in, you don't have to walk it once. You have to walk it every single time. So if the guest virtual address is touching a guest physical address, that is a machine virtual address that has to be translated to a machine physical address, and so on and so on. So you can see the overhead accumulates really, really quickly. So if we back something with large pages, in the guest, we reduce some of that. On the host, we reduce some more. And this is very simplified, right? There are tons of caching structures, and it usually is never the worst case, and it never is, let's say, 20 or even 24 memory accesses just for a simple page walk. It usually is not that bad. But it's definitely more work than it is native. So you might remember this year, this was a table that I've been showing since 2014. And what you can see is that spec JBB 1.3 for guest large pages and host large pages. 30% sounds like a lot, but look at DVD store, only 2%. So let's not, those are all benchmarks. They're running at 100%. They're trying to get every single last drop out of performance out of that, right? And my argument would be, your applications are probably not doing that on a constant basis. Now, in a benchmark, that would tell you how much different it performed, but whether some of your applications potentially need 5 minutes longer or 7 minutes longer, it really, really depends on how time critical that information is to actually have an impact. So all of the numbers that you have seen in relation to large pages usually come from tests and benchmarks, meaning something running at 100% to show a certain maximum impact. Always take that with a grain of salt. Now, obviously, if you have tier 1 VMs, if you have your ERP systems, your SAP HANA, yeah, you will have large pages, right? Let's start with tests, start with dev. But my argument is probably 95% of your prod VMs will not see much of a benefit from large pages. Probably some, but if you're memory constrained, it might be just not worth it. So what I'm saying is, if on average you maybe have like 5% of an impact, CPU cost and performance, is that worth it? Is it even 5%? It's sadly very hard to measure with process and monitor counters. It is very, very complicated. So you can really only approximate. And I'd say, look at criticality of VMs, look at CPU usage, look at memory usage. And by memory usage, I mean our activity heuristic. So how active is it touching stuff? It's really hard to see how TLB miss-heavy a VM is. You can check that, but that is not going to be the only guide for impact. So I actually did create a script that's looking at some VSI counters where you can run it on an ESXi host, and it will give you the amount of shareable pages for those VMs to give you a little bit more insight. There is not a metric that can do that on a vSphere level. So you actually have to SSH into the host. It's not a supported metric whatsoever. But this will give you a certain overview on how much you can reclaim. You can also disable large pages just per VM. Little caveat for that setting, that is only looking at monitor allocations, not at VM kernel allocations. Meaning if you start a VM, it won't allocate large pages, but if you vmotion the VM to destination host, where the VM kernel allocates the large pages during the pre-copy, you will be large page backed again. And we actually did address that in an upcoming release of 7.0, and maybe we can address it in 6.7 as well at some point. Probably not yet by the time you're seeing this, if at all, but we're working on it. What you can also do is you can disable it per host, right? And basically disable it for all VMs on a host, and that works for VM kernel and vmotion and monitor allocations. You can verify that using memstats. So basically you can check the number of backings to see how many large pages are allocated to a VM. Now in this case, I didn't disable large pages whatsoever, and you see the number of backings there is still very high. ×2 is the amount of assigned memory or consumed memory for that VM. Now this here is from an example from a customer I worked with recently, and they're on the larger side. And they said, you know what, we're going to disable large pages. It looked good in the experiments. They reclaimed 200 terabyte. That was about 20% of consumed memory from their approximately 2,000 hosts. So it had about nearly 1 petabyte of memory and reclaimed 200 terabyte of that. Again, that's a pretty large scale example. I'm just saying in what kind of order we're looking at here. And this was, I think, mainly Linux VMs. If you're mainly Windows shop, that number could be a little bit higher. But again, it depends on the workload that you're running. So now let me ask the question again. Would you press that button after everything I told you if you see that the risk is usually minimal, if you can easily restore it, and that you can do it on a per VM basis, more or less, right? I hope I changed your mind a little bit and that you will at least try it out. Maybe start in dev, maybe start in stage. Increase those VM densities. Transparent page sharing still works. It is still there. Didn't even talk about share for salting. Please try it out, increase the density. If you want to know more about sustainability and the reasons and other VMware efforts, please watch Tom's and Nicola's session. Actually, watch it right after this session. because it's all on demand after all. And with that being said, there are more extreme performance sessions that you should watch. The hands-on labs. There is a survey, not for VMworld, but from the actual performance team. So if you go to vmware.com/go/perf, you can give feedback to the actual performance engineers at VMware. So we would appreciate that as well. Of course, we'd also appreciate to fill out the VMware survey. Is this what you want to see? Is it less technical content? Is it more technical content? Is it more jokes you're looking for? Would you like us to bring superheroes back or caricatures? Leave us any feedback that you think is relevant, and and enjoy the rest of your virtual VMworld. Stay safe.